Hello children, this is Chemical Equilibrium Part 2 made for grade 11 of CBSE, ISC, IB and all other boards. In the previous slide we had seen the relation between Kp and Kc that was started, and here it has been written in the exact terms that it should be written in. So we start now. Kp is equal to RT the whole raised to the power C plus D multiplied with N number of moles of C divided by V raised to the power C, number of moles of D divided by the volume raised to the power D, that is the number of moles of D, and this is C is the number of moles of C, divided by RT raised to the power A plus B, number of moles of A divided by volume, because this is concentration. Concentration is nothing but moles divided by volume, raised to the power A, which is moles of A, and number of moles of B divided by V raised to the power B, which is moles of B in the reaction mixture. Now, this turns out to be RT to the power del N C plus D minus A plus B is change in number of moles. And for Nc by V, we write concentration C. For Nd by V, we write concentration D. For Na by V, we write concentration A. For Nb by V, we write concentration B, as was in the equation for Kc. So Kp turns out to be nothing but Kc into RT whole to the power del N, which is change in number of moles. Now let's see how the values of Kp and Kc vary with change in the value of del N. This is del N, change in number of moles. Change in number of moles can be zero. Moles on either side of the equal sign or reversible sign can be equal. In that case, final moles minus initial number of moles, that is number of moles of products minus the number of moles of reactants, can be zero. So if N is equal to 0, Kp is equal to Kc, since any quantity raised to the power of 0 is 1. So Kc multiplied by 1 is Kc, Kp equals Kc. If del N is 1, then RT raised to the power 1 will remain RT. So you have to multiply Kc with something to make it equal to Kp. In this case, Kp is greater than Kc, since two quantities will be multiplied to get Kp. However, if the reaction goes forward with the increase in number of moles, then, or decrease in number of moles, then we have del N equals minus 1 or less than 0. If it is less than 0, Kp is less than Kc, since Kc will be divided by something to get Kp. A high value of Kc indicates that the reaction has proceeded far to the right. That means products are far more than the reactants at equilibrium. If Kc equals 1, the reactants and products are equal in concentration. If Kc is less than 1, the reactants are more than products and the equilibrium is towards the left. Now, Lee-Chatelier principle that tells us how the equilibrium will react to change in conditions to which the equilibrium is subjected to. The principle states if a chemical reaction in equilibrium is disturbed by changing the conditions it is subjected to, it moves in a direction so as to counter the effect of the change. That is, if any disturbance or stress is brought about on the reaction, which is at equilibrium, the reaction moves in direction either right towards the products or left towards the reactants, and it counters the effect of change and restores the Kc. So Kc will be increased or decreased, but the reaction moves in such a direction that the Kc is restored. So we must remember that reaction can either move to the right or the left. Towards the right means products will increase, concentration of products will increase. If it moves towards the left, that means concentration of products will decrease, leading to the formation of more reactants at equilibrium. Changes to equilibrium can be brought about by increase or decreasing the reactants, increasing or decreasing products, changing the pressure, changing the temperature at the equilibrium point, kept this slide vacant to draw two diagrams. The diagrams are like this. This is time and this is concentration. Here we have the reactants and here we have the products, and this is the time, the variation of time. The time increases this way and the concentration increases in this direction. As reactants undergo change forming products, their concentration decreases. At the same time, the concentration of products starts rising. And at a point, the rate of reaction and the product is given by this line perpendicular to the x-axis here. So this is the time when the reaction has reached equilibrium. So this is the equilibrium point. Equilibrium point, or the time in which the equilibrium is reached. Another diagram can be drawn. Another diagram can be drawn, and this shows that the reactant has reached its lowest value, as also the product has reached its maximum value, which can be read off from the y-axis. Here again we have concentration rising in this direction along the y-axis, and along the x-axis we have again time. This is time versus concentration graph. So these are the two diagrams or the two graphs which may be asked in an examination, and this is what it means. These are the reactants. These are the reactants that they have reached a concentration value which has become constant, and this is the concentration value of the products which are constant at equilibrium. Now, let us see the factors that affect equilibrium. Factors affecting equilibrium. Concentration of reactants. If increased equilibrium shifts to the right, Kc is restored and vice versa. That means if the concentration of reactants at equilibrium is increased by introducing more reactants from outside, the equilibrium will go to the right and Kc will be restored. And if the concentration is decreased, then the opposite follows. Concentration of products. If increased, the equilibrium shifts to the left, just the opposite of increase in concentration of reactants. It shifts to the left to restore the Kc and vice versa. If it is decreased, then it goes in the other direction. Pressure. Now let's see if number of moles of products and reactants are the same, that means they are equal, change in pressure has no effect on equilibrium. It neither decreases nor increases. If the reaction proceeds by a decrease in number of moles, an increase in pressure favors the formation of product, because if number of moles decrease, volume will decrease, and that is favored by high pressure. If the reaction proceeds by an increase in number of moles, a decrease in pressure favors the formation of products, and an increase in pressure favors the backward reaction. Addition of catalyst. Addition of catalyst increase the rate of backward and forward reaction equally and has no effect on the equilibrium. Only the equilibrium is arrived at faster. The point of equilibrium will arrive faster. It will take less time to arrive at. Addition of inert gas. Addition of small amounts of inert gas has no effect on the equilibrium. The reason is it neither changes any products nor changes any reactants. It does not react with the mixture which is present at the equilibrium. So its addition has no effect if it is in small amount. However, if the amount of inert gas introduced into the equilibrium system increases the volume too much, then decrease in concentration or increase in concentration might take place, in which case the reaction will move accordingly either to the left or to the right to restore the Kc. So these two things have to be borne in mind. But addition of small amounts of inert gas has no effect on the equilibrium. Temperature. An increased temperature favors endothermic reaction, whereas a decrease in temperature favors exothermic reaction. Because in exothermic reaction, heat is removed. From where the heat is removed, the products are at lesser heat than the reactants. They have lesser energy than the reactants. So this happens. An increased temperature favors endothermic reaction. If the reaction is proceeding forward by absorption of heat from surroundings and you are giving heat to it, so that will favor endothermic reaction. It must be noted that if forward reaction is exothermic, the backward reaction is endothermic. So if the forward reaction is favored by decrease in temperature, the backward reaction will be favored by increase in temperature in such cases. Limitations of Le-Chatelier's principle. It deals with the effect of one parameter in isolation. In isolation, whereas the real reaction is conditioned to by many factors. As we shall see, 3H2 giving ammonia is a reversible reaction. Though it is exothermic, the temperature required is 450 degrees centigrade. And a pressure of 200 atmospheres. The pressure is 200 atmospheres because the reaction is proceeding with decrease in number of moles. We have 3 and 1, so 4 moles are here. 4 are here, and it decreases to half. Therefore, higher the pressure, the more it will move to the right side, or the equilibrium will move to the right side, producing more ammonia. But producing high pressures requires energy, and the cost of ammonia will go up. So 200 atmospheres is taken as a cutoff quantity, and the pressure is maintained at 200 atmospheres, below which nitrogen will not react with hydrogen. At the same time, we have catalyst, and it is supported on molybdenum. It is supported on molybdenum, which is a promoter. The promoter enhances the efficiency of catalyst. So this reaction cannot be studied in isolation with any variation of any particular parameter, because it is conditioned to the optimum yield is when all these three factors are met. A temperature of 450 is necessary, even though the reaction is exothermic, to make nitrogen, which is very unreactive, react with hydrogen. So, some problem. How is liquid vapor equilibrium attained in a closed vessel? The molecules on the surface of the enclosed liquid have a greater kinetic energy as compared to those inside the body of the liquid. So the molecules having higher energy, they tend to fly away into the space above, producing the vapor. But as they go into vapor state, they lose energy and they again return to the liquid state. The other molecules that have replaced the molecules escaping from the surface, they come to the surface, they also do the same thing, and at a given temperature in a closed vessel, a equilibrium established between the liquid molecules and its vapor counterpart. Another very interesting question which is normally asked is, why can't equilibrium be established in an open vessel? This is due to the loss of matter to the surrounding. The concentration of the product keeps decreasing as the matter produced is lost to the surrounding. Therefore, the forward reaction continues and the equilibrium is never reached in an open vessel. It is one-sided reaction. Some concentration of product is required to initiate the backward reaction, which is not met with in this case of an open vessel. There's some numerical. Number one, write down the equilibrium constant expression for the following equilibria. One is 2NO gas plus oxygen gas gives 2NO2. Second is N2 plus 3H2, we just discussed, gives twice NH3. And the third is calcium carbonate reversible with calcium oxide plus CO2 gas. So for first, Kc is given by squaring the concentration of nitrogen dioxide as in the numerator, and then divided by concentration of NO to the power 2 because we have 2 as the coefficient here, and oxygen has no coefficient, that is 1, so multiplied by concentration of oxygen. This 2 should be down. This 2 should be here and not here. Kc for the second reaction, nitrogen with hydrogen, is concentration of ammonia squared divided by concentration of nitrogen into concentration of hydrogen cubed. In the third case, if you see, we have 2 solids and only 1 gas. And we know that the concentration of solids do not increase or decrease, and it remains unity, 1. Therefore, Kc is equal to concentration of CO2 only. Now, for a general reaction, 2A plus B reversible C plus 3D, del H is plus X kilocalories. What will be the effect of decrease in volume? Remember, we have not included the parameter of decrease in volume in the study in the previous slides. Increase in temperature and increase of pressure at equilibrium. Now let us answer. According to Le Chatelier's principle, when the pressure on a system at equilibrium is decreased, the equilibrium will shift to the side of the reaction that has more moles of the gas. This is because decrease in pressure causes an increase in volume and vice versa also, which lowers the concentration of the gas molecules. The system will try to restore the equilibrium by producing more gas molecules which increase the pressure. For example, consider the following reaction. Since the reaction, and the following reaction is here, since the reaction is exothermic, the equilibrium will shift to the left with increase in temperature. So it says increase in temperature will shift to the left, as we have mentioned in discussion of the Le Chatelier's principle. Increase in pressure will favor the formation of reactants because that is where volume is less, 2 moles plus 1 mole, and here we have 1 mole plus 3 moles, so 4 moles this side on the reactant side and 3 moles on the 4 moles on the product side and 3 moles on the reactant side. And I hope you will solve more. Let me know if there is any problem in solving. We'll give you the solution and we will explain it also on the slides. Thank you very much for watching. Please do subscribe and like and comment. Comments are very, very necessary for me, for my improvement. So please comment on these videos. Your comments are most welcome. Thank you very much. Have a nice day.